anyhow, it's, it's still an efficient way, okay? For these kind of examples, cobalt is very close to the ideal silver A ratio, okay? But as I mentioned, the HCP structure is not the most important thing. Yes?
How is zinc higher than the ideal?
You mean, that's more like, how to say that? That depends on the, manufacturer, say for example, how strong of the electron, cloud repulsion, how much of the screening of the charge of the nuclei by the electron. Most important thing for those kind of key metals, zinc is the transition metal. The 3D orbitals occupies a lot. That plays a very important role here. The arrangement, if you think about the electron configuration there, zinc is toward, it's underneath copper, so it's nearly completely filled. Okay, so, but the cobalt, that is in the center of the key metals series. So that one has more unfilled 3D orbitals here. Okay, that's related to that. But that's beyond this class. Okay, so anyhow, that's this slide summarizes the three most important unit cells, right? BCC structure, atom per cell, we know that 2, right? Center 1, 8 corner contribute 1. FCC, 6 face-centered atoms contribute 3, plus the 8 cornered one, so here are 4. HCP is different, I didn't talk much about that one, but think about, you have those kind of hexagonal packed 12 corner atoms. Each of that will contribute 1, 6. And also you have 3 center one, remember between the top and the bottom layers, you have 3 atoms within the unit cell, right? So that one actually we have 6 atoms per unit cell. You don't need to worry too much about that, okay? Especially don't worry about the number of atoms for the HCP structure. Coordination number, we talk about the BCC 8, center 1, actually the neighbors, you have just 8 corner atoms, so that one has 8. FCC is even, 6 surrounding, 3 top, 3 bottom, that's 12. HCP also 12, okay? And the most important thing I want to show you is FCC and HCP are the mostly close packed, densely packed, 74%. BCC another densely packed, but lower than the FCC and the HCP, right? And as I mentioned, FCC and HCP, they both have 74% of the packing, but their structure is different. The difference is FCC is ABC, ABC. HCP is AB, AB. Why that? Is because of the voids, okay? Think about the bottom void, the bottom layer. If we think about the hexagonal layer, the bottom one, in those kind of voids, that's, air as there before. If you think about it, we have 2 types of voids. So they're almost identical, just depend on their location, okay? So if we think about these kind of voids as A voids, this layer, think about these layers of voids as A voids, then the nearby one, or below the top layer, we call that a B void. And then this one has A voids again, and then these are the B voids, okay? So think about that. If you have the bottom one, when we consider the second layer packing, if the second layer spheres takes the A voids, okay, so that means they take these layers of voids of the bottom layer. Okay, think about that. So that means the second one, we always think they take the A voids. Okay, then if the third layer retake the A voids of the B layer, of the second layer, okay, if they take the A voids of the second layer, that A voids, say for example, think about here, here is A void. Okay, here is A voids of the second layer. That A voice, when you put a particle in that location, that particle has exactly the same position as the very bottom one. Okay, so by that means, if we think about, if they take the A voice, the third layer will be in a different location. So by that means, if the third layer takes the A voice of the second layer, then you will get A, B, C structure. The third layer has a different location than the bottom one, than the very bottom. Okay, so then you have an A, B, and C structure. But if the third layer takes the B voice of the second layer, in that case, the third layer will actually corresponding well to the bottom atoms. So by that means you have A, B, but now you have A. And then if you continue to build on, you have another B. So therefore, the HCP structure, you have AB, AB. FCC structure, you have ABC, ABC. The only reason is because of this kind of voids. When you put, depending on the location, where do you put the next layer, or either the A voice or the B voice. Okay, then you can get either FCC or the HCP structure. Okay, so that's you don't really need to know about the A voice or B voice. The most important thing you need to remember is FCC you get ABC, ABC repeating, HCP you get AB, AB repeating. But they both are very efficiently using the space. 74% is their, APF. Okay, so that's one thing. Where important thing for the crystal structure, the crystal lattice structure. You need to know. You only need 14 different types, and you don't really need to know which 14. Okay, that's way too much. But you need to know if I gave you one, say for example, cubic, center cubic cell, how can you get the volume fraction? Okay, how much space being occupied by the atoms? Okay, you need to know that. And also need to know the major difference between FCC and HCP structure. Okay, now let's talk about another important thing, okay? So when we talk about the crystals, how do we define the different crystal plane? How do we define, say for example, what is the position for the different atoms, okay? So indeed, when we talk about these kind of topics, we always use a Cartesian coordination system, okay? So as I mentioned to you already, x direction, the positive, that's very important, okay? You need to know about that. The x direction, positive x-axis is pointing out of the screen toward you. Okay, that's a positive direction of x. Y is toward the right of the screen, okay? And then that's a positive y direction. Z is pointing up in the screen, okay? So that's very important. You need to know this definition. This is a little bit different than the definition in other chemical engineering classes, okay? So the x direction, positive x direction is pointing out, okay? So by that means, once we define that one, once we know the origin of the Cartesian system, then everything becomes straightforward, okay? So say for example, if we want to define the position of this atom, what you need to know, just know what the numbers corresponding to this coordinate, right? This corresponding to what? X-axis is, here is the origin, is positive 1. So we use 1, comma, y-axis, if you draw a line toward the y-axis equals to 0, z equals to 0. So therefore, this position, 100. This position is what? Projection of that one along the x-axis, 1, y-axis, positive 1, z-axis, positive 1, this location, 1, 1, 1, right? This location, 0, 0, 1, because x, y projection both 0, what the direction is what, positive 1, right? So it's easy. What do you think if we move along that way? 1 unit along that way. What the position? Coordination?
0, -1, 0.
X equals to 0, right? -1,
And 0.
0, right? So, okay, that's easy. Okay, so the only thing you need to remember is x-axis is pointing toward you. That's a positive x direction. Okay? So that's very easy to do. And then based on that, the next step, once we know the position, the coordinate of the position of the atoms, then we can define the direction indices. Okay, direction indices indicate what? Indicate a kind of like a line, a direction. Okay, a vector. Okay, so in that case, also very straightforward to calculate that, to define that. Well, see, for example, from the origin to this point, diagonally, pointing that one, direction of that one, but in this case, when we define the vector, or means the direction, we use square bracket. Okay, that's something different. That's different than the position or the coordinates of a point. Okay, in that case, we use the parentheses, we use a comma to separate that. Okay, so think about that. This system indicates the location or the coordinates of the atom. Easy, right? Because that one is well defined. You know how to do that. And then when you see this kind of a square bracket, there's no comma in between that. That's a vector. That's a direction. Okay? And you see that here I gave you 4 different direction vectors here. Okay? So how do we calculate that? See, for example, when you see a vector pointing from the origin toward a point, here, what the coordinates of this point is? This one is 1/2. X equals to what? 1. Y equals to 1/2. Z equals to 0. Okay? We know this location, we know that. Coordinate is 0, 0, 0. How do we define that one? Just follow this step. Okay? Easy, very easy step. Okay, let's take a look. Now let's do another example. For the vector pointing from the origin to the location, 1, 1, 1, 1, 1/2, 1. Okay, because this one is x-axis is 1, y-axis is 1/2, z-axis is 1, right? Okay. To determine the direction indices of this vector, what you need to decide, first one, the endpoint. What's the coordinate of the endpoint? Or that means at that point, this vector pointing out of the unit cell. Okay? We know that one already, right? It's labeled here. Origin is this. Then what you need to do, the first step, we have already done that, and then you subtract the coordinates of the points of the emergence, or that means the endpoint, by the origin, by the starting point. Okay, you subtract the coordinates of the endpoint from the starting point. Then we will do the simple calculation. 1 minus 0 equals to 1. 1/2 minus 0 equals 1/2. 1 minus 1 equals to 1. So therefore, using that, we finish here, okay? Then you decide if all these numbers are integer or not. Apparently not, because there's a 1/2 there, right? Then what you need to do, just multiply by, try to find a number, multiply by all of these 3 numbers, you will get the smallest integer here. You can find, multiply by 2, right? Then once you multiply by 2 every number, 1 equal to, multiply by 2, you get 2. 1/2, you get 1, 1, you get 2. So therefore, this vector, this directional, or this direction indices, the indices is, don't forget, using the square bracket, is 2, 1, 2. That's it. Okay? So if you want to decide the direction indices, or that means the vector that's pointing toward a plane, what you need to do, just follow the endpoint, coordinates of the endpoint and the starting point. to subtract the starting point from the end point, and then decide if they're simple integers. If not, then multiply by something, then you will get the final. Okay? So one example here, if I want you to decide the direction index for this direction, for this vector, starting point is here. Okay? Number at least there. You need to know how to determine these numbers. Okay? And then the end point is there. That means from this point, the vector we're protruding out of the unit cell. And then what you need to do, subtract the endpoint coordinates from the original one, you get these numbers, right? But don't forget, here you get a negative number. Okay, this is the first time you see a negative number. Okay, don't worry about the negative number. Okay, you get the negative 1/2, 1/2, 1/4. The smallest number you can multiply this set of numbers to get the smallest integers is 4, right? Multiply each number by 4. This one produces -2, 2, and 1. So you get -2 to 1. Okay? To represent the negative numbers, we just write a bar on the number. That indicates it's directing toward the negative direction. Okay, so but anyhow, once you get this number, to writing the direction, these directional indices, we use a square bracket and use a 2, but using a bar above that one that indicates a -2 and 2, 1. Don't forget, you do not use comma here. Yes?
Can those numbers be greater than 9? Or they're restricted to 9?
Be greater than what? Than 9?
Yeah.
It could. It could be very complex. It could. Why not?
But then how do you know which one goes to what? No, but in that thing, then you wouldn't know. Like,
what do you mean? What do you know? You know, it could be, see, for example, could be 18 to 1. Think about that. How can you get 18 to 1? 18 to 1 means what? Means this number. Think about that.
What?
It could be any number here. It could be any number.
Yeah, but how do you know if it goes to the x or the y or the z if it's greater than 9? Because then you have 4 numbers.
I don't understand you. Why? How could you get the 4 numbers? How could you get 4 numbers here? You only have 3 numbers.
Yeah, that's what I'm saying. If one of them goes up to 10,
digits.
yeah.
4 digits.
If the reference, if there's 0, 0, and then it's to 10.
It's okay.
But then how do you know which one does it go to when you do that, the direction? Because then you have 4 digits there.
You get 4 digits here.
Am I asking?
No. Oh, okay. I understand what that means. Okay. So that's a good question.
So that would never happen.
That's a good question. See, for example, the question is this. Okay, I think that's a good one. Okay. The question here is if a number after this calculation, see, for example, if this one is 10, okay, 10 to 1. If you represent that one here as a 1, 0 to 1, right? What does that mean? Or it could be, you know, something like a 0, 1, 0, something, right? What do you guys think? That's a very good question. What do you think? Is that possible or not? My question is.
Yeah?
It's possible, right? Why it's possible is because you could get a 10 here if this number is very small, right? Or you know, if that one is very large. See, for example, it's 5. You know, see, for example, if we think about actually, it's not possible.
All right, that's what
Right? It's not possible. Okay. You know, the reason for that is because of this. If you think about a number larger than a certain number, if you want to get a very large number here, that means the end point is where? Is pointing toward a far point outside. Think about that one, right? Only that way you will get a large